The Nobel Prize in Physics 2007 is awarded jointly to Professor Albert Fert, Paris, and to Professor Peter Grünberg, Jülich, for the discovery of giant magnetoresistance, GMR. 150 years ago, Lord Kelvin, Professor Thomson, reported on his experiments with centimeter-sized pieces of iron and nickel. He found that when subject to a magnetic field in this direction, say, the resistance increased parallel to the field and decreased perpendicular to the field. This was a discovery of what one could call a microscopic anisotropy. This year's Nobel Prize in Physics is about another type of anisotropy, one that shows up on nanometer-sized layers of ferromagnetic and non-ferromagnetic materials. Electrons with different spins, down, up, scatter differently in the boundaries of these layers. More scattering gives a higher resistance. It is the spin-based explanation of GMR that has led to the use of the term spin valve for various GMR devices. The 1988 discovery of GMR turned the study of layered magnetic structures into the most dynamic field in physics. Application came quickly. The size of magnetic storage devices has dramatically shrunk. Today, over 1 billion read heads in computer disks use GMR, giant magnetoresistance. A new field, spintronics, has emerged. With GMR, the areal density of magnetic storage doubled every year after the introduction of GMR. The 1988 discovery of GMR shows how results of basic research turn into important applications. It is now a pleasure for me to introduce to you the first of this year's physics laureates, Professor Peter Grünberg. His thesis from 1969 at the Darmstadt University of Technology was on absorption and emission spectra of samarium. Since 1972, he's performing research at the Solid State Research Center in Jülich, and since 1992, he is an adjunct professor at the University of Köln. In 1986, Professor Grünberg discovered antiferromagnetic interlayer exchange coupling, published in Physical Review Letters, a paper cited more than 1,100 times. With this discovery, the stage was set for GMR, and Professor Grünberg's GMR discovery paper from 1988 in the Physical Review belongs to the most cited and well-known papers in condensed matter physics. Exploitation of GMR effects has led to 8-figure earnings from royalties for the research center in Jülich. Professor Grünberg has received numerous prizes, including this year the Japan and Wolf prizes, both together with Professor Fert. Bitte, Professor Grünberg.
Good morning, ladies and gentlemen. Welcome to the Nobel Lectures in Physics, which will be given by Albert Fert and myself. I will get started. And you can imagine this is a great moment for any physicist to stand here and give a Nobel lecture. And accordingly, I'm also still kind of nervous. Okay, so here we are. Let's see. Yeah, okay. So I've given the title of my contribution from spin waves to giant magnetoresistance, GMR and beyond. As you will see, in fact, we called it enhanced magnetoresistance. We'll come back to that later. And by introduction, I mean that I will introduce myself in a way, what my background is, education and so, but only briefly. Then we'll come to various discoveries where one can say one discovery sort of initiated the other. It started with the discovery of brilliant light scattering from Dayman-Eschbach surface modes. I will briefly explain what I mean by that. Then this one initiated another one after some time, which was the discovery of interlayer exchange coupling. The chairman addressed it already, in fact. And that by itself then initiated still another one, which was the discovery, as we called it, enhanced magnetoresistance. Now it's known under the term giant magnetoresistance, which Albert Fert brought up to this kind of nomenclature. And then briefly I will also talk a little bit about further developments. I will not talk too much about tunnel magnetoresistance, but it is a further development. And then a little more about current-induced magnetic switching, because we continue to work on this now in Jülich. Show two examples. And finally, also very important, also in the context of the price, is applications. So I will talk also about applications. Okay, so I would like to introduce myself by this one. I finished my thesis in Darmstadt, my PhD thesis in Darmstadt in 1969. The title of my thesis was Optical Spectroscopy and Crystal Field Analysis in some rare earth garnets. That was done under the supervision of Professor Stefan Hüfner, who is also here in the audience. And our joint mentor at that time was K.H. Hellwege, director of that institute. After that period, after the PhD thesis in Darmstadt, I was on a postdoctoral fellowship in Canada, in Ottawa in Canada. And my research topic at that time was Raman spectroscopy on electronic states and phonons. So here I worked with visible light, here I worked again with visible light, but here with light scattering, whereas this was absorption and fluorescence spectroscopy. So, but in both cases it was mainly with light. My supervisor in Canada was Professor Koningstein. Then, since 1972, I was at the research center in Jülich in the Institute for Magnetism, which was founded in 1971. I joined the institute at 72, so it was a newly founded institute, and we had the opportunity to build up some new equipment also. I will come back to that in a minute. And we were mainly occupied with the investigation of magnetic semiconductors like europium oxide and europium sulfide. And then I tried to apply new experimental methods to the investigation of these materials in the first phase. So I was occupied then with the fabrication and magnetic transport properties of layered magnetic structures that developed a little later. My mentor at that time was Werner Zinn, director of that institute. Okay, so now let's come to the first topic and to the first discoveries, which then initiated the other ones. As I said, we had the opportunity, great opportunity in a newly founded institute to build up some new equipment. And at that time, there was a very exciting new instrumental development initiated by John Sandercock in Zurich. That was the multipass Fabry-Perot interferometer, which one can use in a light scattering experiment, similar to Raman spectroscopy, but here it's interferometry, to investigate collective excitations in materials. And since we were working on these ferromagnetic semiconductors like europium oxide, we applied it to these. And here I show you one of the first spectra we got. This is a light scattering spectrum from europium oxide, showing the bulk spin waves of that material. These are the green peaks, which in a light scattering experiment you can always observe on the anti-Stokes and the Stokes side. And the shift from the elastic scattering gives the frequency of that excitation by itself. So what we expected, we saw in the green lines here, this is the bulk scattering from the spin waves in europium oxide. But then there was always some additional peak indicated here in red. And first it was a big puzzle for us what that means, this additional peak. And it showed also a very strange behavior. in that when we reverse the magnetic field here, in that experiment it is supposed to show up, but when you reverse the magnetic field and the magnetization, then this additional peak jumps from the anti-Stokes side to the Stokes side, as you can see down here. So for some time that was a puzzle, until we found out that this is related, as I said before, to the sense of the magnetic field, and the solution to the problem is you have to know that Stokes and anti-Stokes scattering for a collective excitation is related to the propagation direction, and if something appears only on one side of the elastic scattering, it means it propagates only in one direction along the surface of our sample, so which is the case here. When you turn the magnetic field around, it propagates into the opposite direction, and accordingly this additional line appears then on the Stokes side. So after we had found that out, we knew that we had observed the so-called Damon-Eschbach surface mode with its unidirectional behavior along the surface, where this is always also related to appearance Stokes and anti-Stokes shows the propagation direction. Okay, so we were very excited about that. Other people said, well, this is well known, that's the famous Damon-Eschbach mode, which you have seen. You have seen the first light scattering experiment, okay, but the mode itself is known. But then there were always some encouragement. Yeah, here we are. In that this example, this experiment later appeared also in a book on solid-state physics by Ibach and Lüth. So we were very much encouraged that this was taken as an example of modern magnetism and modern research in magnetism, and was taken into a textbook. Okay, so then we continued with the studies of these Damon-Eschbach modes and went into the treatment and observation of coupled Damon-Eschbach modes. So we are building up now, and not taking only one layer, but make a system consisting, for example, here of two magnetic layers separated by the interlayers. And here at this point, I arrive already on the experimental structure, which we will continue to investigate in the following. So we call that always magnetic double layers, two magnetic layers separated by a non-magnetic interlayer. And then we studied these Damon-Eschbach modes and their couplings in these layered structures, and came up with a calculation. In that calculation, the most important ingredient is the Landau-Lifshitz equation, which you have to evaluate, and certain boundary conditions. And then you can calculate the frequencies of these coupled Damon-Eschbach modes. Here is shown for Stokes and anti-Stokes scattering, because we have seen already that reflects the propagation direction. So the propagation direction here on this side and on this side is in the opposite direction, and is supposed then to show up again in Stokes and anti-Stokes scattering in the light scattering experiment. And indeed, you can see here the experiment which proves that this calculation is right. If you have a large separation, the D0 here is large, then you can get almost double degeneracy at the frequency of the Damon-Eschbach mode of the single film. That's out here. When you decrease the interlayer thickness D0, you get a stronger interaction, you get a larger splitting of that mode that corresponds to the value D0, which corresponds to this place here. Okay, so then that was proven then also by the experiment, and we were very much encouraged that this calculation then is right. And then for fun, we started also to calculate what happens if we turn the magnetization around and give it the same treatment with the Landau-Lifshitz equation here. And then we came up with the prediction, which is shown here, that Stokes and anti-Stokes frequency are expected to be different. That is shown by these branches. The corresponding frequencies are different. But in the first time, after we found that, we were not able to do the experiment. We had no reliable means to have a system where we have the anti-parallel magnetization direction. So that had to be left blank here. There's a white spot on the map in our spin wave studies. Okay, but I will come back to that later. You'll see that we finally found also that. Now I'm telling you something which was some sort of an unknown, well, the question was known, but the result was not known. There was a puzzle about coupling phenomena in these structures. I show you here again such a structure consisting of two magnetic films separated by the interlayer. And we assume that the interlayer is very, very thin. Then you expect that at some point, at some thickness, you will have holes in the interlayer, which can be filled by magnetic material, and you can get magnetic bridges in these structures. And then you would expect that this leads to ferromagnetic coupling. They would align parallel. So that is called pinhole coupling. Another possibility was discussed in the first place by Niel, that one could have also, even if we have a closed interlayer here, but it is meander type. There's a meander type. This meander type is also called an orange peel, and the corresponding coupling was called orange peel or Niel type coupling, and one can easily show that this also leads to ferromagnetic coupling. But there were not many experimental methods really to find that out, to establish that, to make sure that this is present, or what kind of other coupling there is. And so we found that our new method, by looking at the spin waves, could contribute to this question. We had a new experimental tool available to study just this question. So I introduce you to this now here. What we expect, what could happen if we have this pinhole coupling or the meander type. Here I show you the pure, again, the picture which one expects for pure dipolar coupling. So this coupling comes about because in the individual magnetic layers, the magnetic moments precesses and generates stray fields in the other film, and this way, and vice versa. And this way they couple due to the dipole-dipole interaction. But if you decrease the interlayer thickness, which is supposed to be here, you have decreased, at some point you expect that the real or this pinhole coupling or other couplings set in, which lead to ferromagnetic coupling. And then you can predict, this is not the result of a calculation, but it's more qualitative, that the lower branch in that picture here, which is true for the pure dipolar coupling, would shift upwards, and you can expect that because when you take the interlayer completely out and you have again a single film, you know already what you expect for the spin wave frequencies, because here, for that case, the lower branch would not be there at all, but we would have the upper branch here, and we would have a single frequency at the first standing spin wave mode of the combined system. So for the single film, you know the result, and you can predict then this lower branch, if you switch on the spin-hole coupling, should shift upwards into the position of the first standing mode. Okay, so we realized that now we have a new tool available to investigate this question, and so we did. And here I show you now two examples of such experiments. First, let's assume we have here again our layer structure, and we have for the interlayer now gold. Then let's start with the picture here with the large thickness of the gold interlayer, 20 angstroms here supposed to be. And then we observe what we expect, in fact, also from the dipolar coupling, because there is no pinhole coupling yet here. We expect the lower mode to be in this position at a low frequency, and the upper mode, which is indicated here in red, corresponds to the branch here. When we decrease the interlayer thickness, here it's only 12 angstroms, this one shifts downwards, so we are still on this branch here. But when we take the interlayer completely out, and we have arrived here at this point, and we have the high frequency which corresponds to that point, and the other one essentially always stays in the same place. Then we did the same experiment with chromium interlayers, and if you have a large thickness of the interlayer, you are here, you in fact get something which is very similar to the gold interlayer with a large thickness. So it's the decoupled case, we are still here. But when we now decrease the interlayer thickness, the chromium thickness, something very strange suddenly happens. This one shifts not upwards as it was for the gold here, but suddenly it shifts completely downwards and comes to a very low frequency. And so looking at this spectrum here, I really remember that very clearly. I looked at it for a long time and I thought, do we really see here antiferromagnetic interlayer coupling? And it turned really out to be true that this low position of that frequency, I'm sharing this impression now at the moment with you, indicates that there is antiferromagnetic coupling. And this can then later on, well, we did that in more detailed treatment, can also be called a soft mode behavior of a mode which initiates the phase transition from ferromagnetic to antiferromagnetic. That is, then generates a very low frequency of the corresponding mode here. So that was the discovery of antiferromagnetic interlayer coupling. And now we were encouraged to repeat that experiment as I indicated before. So, because now we were able to produce such structures where we have the anti-alignment, opposite alignment of the magnetization on the individual films, and do the light scattering experiment. And I show you here the theory again, which we did before. Different frequencies, Stokes and anti-Stokes, and indeed this is what you see here. And after we got this spectrum, we were really sure that now we have seen, we have produced layer structures with antiferromagnetic interlayer coupling and get the anti-alignment of the magnetization and see the corresponding light scattering spectrum for the anti-aligned case. Okay, here I show you another picture from my lab book at that time. In fact, I got the first examples when I was on a sabbatical leave at Argonne National Labs in the United States. That was in May 1985. We completed that. We did many different, this is for the iron chromium iron system here. We did many experiments, as you can see here, the experimental points. These are all the frequencies which are plotted as a function of the chromium thickness here. And later on, we also were able to do a calculation and extract a parameter, which we called A12, which is defined by this expression for the interlayer exchange energy. And one can evaluate from these frequencies, these are still frequencies, one can evaluate the size of that parameter and plot it as a function of the chromium interlayer thickness and get this one here. Now you may note that here we see in fact already oscillatory coupling, which was established somewhat later than also by Stuart Parkin. He confirmed this. At that time we saw it in this example, but were not able to reproduce it. So in our first publication, in fact, we left that out because we were not so sure. We were sure about that first peak and the soft mode behavior and the corresponding antiferromagnetic coupling, but not about that second peak here. And you can see here it does not appear in this evaluation of the frequencies. Good. Okay, so one can say at that time the time was really ready for discovery of interlayer exchange coupling, because at about the same time it was discovered by others in other systems, of course. These are two rare systems here, oscillatory coupling in gadolinium yttrium multilayers by Majak et al. Another work also in rare systems by Salomon et al., helical structures in dysprosium yttrium. I don't go into the details of this, it's a bit more complicated. But eventually it's all so-called Ruderman-Kittel type coupling, interlayer exchange coupling, in the same way as it is interlayer exchange coupling here in that example which we found for the iron chromium structure. Okay, so you can see sometimes the time is ready for a discovery and it is discovered at the same time in different places. I would like to give you only a short feeling about the mechanism which is behind these coupling phenomena. And I do in a very simple way, and well, the mechanism which leads to that was explored by a theoretician like Patrick Bruneau is also sitting here, and it was called the Fabry-Perot model of the interlayer exchange coupling. And it relies on reflectivity of electrons in the interlayer. Again, you have the cross-section here, you have the magnetic films on both sides. And then electrons always pass from one film to the other across the interlayer, and you get multiple reflection in the interlayer, which is spin dependent, so sounds rather complicated. But these multiple interference effects, which depend also on the thickness of the interlayer, give rise to this type of coupling. And since it depends on the interlayer thickness, it's reasonable that it oscillates also as a function of the interlayer thickness. Now I show you here again the Fabry-Perot. As I said before, that is called the optical Fabry-Perot. No, sorry, the Fabry-Perot, we are up here. The Fabry-Perot model of interlayer exchange coupling, and it was funny for us that we discovered this type of Fabry-Perot model with a real Fabry-Perot, with an optical Fabry-Perot. And here you see how that works. Also multiple interference effects for the light reflecting back and forth in the cavity of this Fabry-Perot. So it's a very similar effect, only in that case with light, and in that case with electrons. So one Fabry-Perot has discovered in a way the other. Okay, so now comes the break, sort of. Now we were wondering, now we have established these type of couplings. We have antiferromagnetic coupling. So now we wonder what else can we do with that? And then we moved into a new field, namely transport in these structures, and applied to our structures which we were now able to prepare. The preparation was, so to say, ready for this new field. And before I go into the transport phenomena, I'm sure Albert Hertz will talk about that in more length. I just want to indicate to you that you have the right picture, the right idea about what happens when a current flows in a material. I present you here the MOTS2 current model, which describes magnetic electron transport or resistivity in ferromagnetic materials. One has first to accept that in ferromagnetic materials, the spins of the electrons are either down or up, and these orientations are so stable that they are maintained during the flow of the current. During the current, the electrons flow in one direction, drift in one direction. They are scattered very often, but this orientation of the spins is rather stable, and that leads to MOTS2 current model, which can also be described by an equivalent circuit in this way: two currents in parallel for spin up and spin down, and the resistance in each channel is determined by the individual scattering rate. So with this idea, then we went into this new field of transport phenomena, and I would like to show you by a computer animation what we expected now, because now we have that tool of antiferromagnetic interlayer coupling. So we can, for low fields, have the magnetizations of the individual films anti-parallel. I will come to that in the next picture, in fact. But if for a high enough field, then you get this situation. You can align the magnetizations of the individual films parallel. And I would like to start with my animation now with this situation, that they are parallel, and make the animation here. So I take from the many electrons which are drift in this direction, I take only one as representative. And what we expected is that there is not very much happening when these electrons cross from one film to the other across the interlayer, because the magnetizations are parallel. They find the situation on both sides, same situation on both sides. But when we turn one magnetization around and do the animation again, then we expect that there is strong scattering, because there should be now more reflectivity of the electrons coming to that side, and also more scattering. So since the scattering rate determines the resistivity, we expected to have an increased resistivity here in this situation. Okay, so then we did the experiment under various conditions, and indeed could show that this is really the case. I show you here essentially two experiments where we always made sure how is the remagnetization curve of the films when in an external field. So these are again these double layers For the transverse measurements, which are shown in the lower part, we have to add contacts on both sides and measure the resistivity for a current flowing in the plane of the sample. But in the upper part, we see the result of a hysteresis or remagnetization experiment. That is done by means of the magneto-optical effect, which is roughly speaking the magnetization of the sample as a function of the external field. So here we have high positive fields in one direction. Here we have it in the opposite direction. So scanning the field back and forth, you run through the so-called hysteresis curve of the sample or remagnetization. And I showed you before already these asymmetric light scattering spectra. We confirmed that in this plateau we have anti-parallel alignment by means of the light scattering experiment, and for the lower plateau also we have anti-alignment, but it's reversed compared to this. So both are turned round by 180 degrees, and that we were able to confirm by means of the light scattering spectrum, as I showed you before. Then now we really do the transport measurement shown in the lower part here, and we can identify a high plateau, a high resistivity with the anti-alignment taken from that experiment. Okay, so we have a strong increase of the resistivity when we have the anti-alignment as established by the other experiment. Now since our samples were epitaxial and show the so-called cubic anisotropy of the iron, we were also able to apply the field in another orientation, and now instead of a jump of the magnetization at these places here, we get now a continuous rotation of the magnetization. In one direction it is saturated in the negative field orientation, on the other side positive, and in between it rotates into the anti-parallel alignment. And accordingly, the resistivity then is increased when we have the anti-alignment as is shown here. So it confirms this, that due to the anti-alignment, the resistivity in this structure increases. Now in our, okay, maybe I show that a little later because I have this comparison. Now in 1988 we had a satellite conference of the big ICM conference in Paris that was in Le Creusot, the conference on thin films and surfaces, I think it's called, yeah. So this is the conference crew here, and this is where I met Albert Fert for the first time, and we exchanged our results. We had both presentations and presented our results on these resistivity measurements. And so I became aware of his results and he of mine, and we discussed that we obviously had found the same effect, only that we had only these double layers and the effect was a little smaller, well not a little but appreciably smaller. You can see the comparison here. This is the curve I showed you before, and this is his result. I probably will come back to that result later. Here the effect, if you have a look in more detail, you have a much stronger effect, but these were also multi-layers, whereas we had always only these double layers. So here the effect was only 1.5%. Later on I found that this is a typical value for this thickness range and for the double layers. You never get much more than you maybe get up to about 2, but this is a typical value. Okay. Now at the same time when we did that, we were also able, our chairman indicated already the anisotropic magnetoresistance effect found by Lord Kelvin, Michael Thomson at that time still, which is the difference in the resistivity for a current flowing perpendicular to the magnetization and parallel to the magnetization as a difference in the resistivity. And we were able, for these samples, of course, that's not very difficult, to measure also the anisotropic effect, leaving now the interlayer completely out. So a single film, but about the same thickness as the overall thickness of our layered structure here. And this is the anisotropic effect then of a single film of 250 angstrom thickness of iron. And now at that time there were many discussions to bring this effect into applications in the hard disk drives. IBM was very active in all magnetism conferences, including the one in Le Creusot. There were big discussions how one could do that, how one could improve and so on. So that was discussed for the application. Then we saw our new effect, and so that's much bigger, so that must be also good. If this is good, then this must be even better. That encouraged us also to file a patent suggesting to bring this into the application for magnetic field sensors. That worked out to be quite successful. Okay, now coming back home, I had two very capable theoreticians at that time in Jülich as my guests, Bob Camley from the United States, Josef Banasz from Poland. And they got immediately to work and treated this case of these magnetoresistance effects by means of the Boltzmann transport equation, and fitted the theory or fitted parameters to the experiment. I'll show you some here, some results. Here are our experimental points and the theory based on the Boltzmann diffusion equation adjusting certain parameters. Here, this is the other curve, which I showed you already before, also quite nice agreement, except the anisotropic magnetoresistance effect they did not consider in their calculation, so this makes the difference here. But most important are these figures here, these parameters. They identified this by fitting the theory to the experiment, that it is mainly scattering, spin-dependent scattering of electrons at the interfaces, which is shown here. So the difference in the diffusive scattering parameter shows up in this figure here, this approximately 0.5. Half of the electrons with spin up are scattered at that interface, whereas for the spin down electrons, it's a much smaller fraction which is here scattered. And this difference finally can explain this magnetoresistance effect, whereas for the mean free path of spin up and spin down electrons in this evaluation we have almost the same. So that does not explain the effect, but it is the diffusive scattering at the interfaces and the spin dependence. All right, maybe I skip that because let me see how we're doing in time. Yeah, I think I should really better go on, otherwise I might. No, sorry, I cannot skip that. That is important. Okay. I said giant magnetoresistance and beyond. Now we are at the point we are talking about beyond. What is beyond now? Well, there are certain effects. Maybe I should indicate that anyway. Yeah. No. Here, this is all beyond. Well, this is still repeating interlayer exchange coupling. Here I said multiple interference effect of electrons in the interlayer, giant magnetoresistance, spin-dependent scattering at interfaces mainly. So here I repeat what I said before. This is now beyond tunneling magnetoresistance. One finds also that if you have a structure with an insulating interlayer, the tunneling probability of electrons with spin up and spin down is different. That also can be used for sensors in a very similar way as for the giant magnetoresistance effect, only that you come to much higher percentage here in the resistance change between parallel and anti-parallel magnetization alignment. But I do not want to go into the details of that. I would like to treat this one, current-induced magnetic switching. And there I have an animation which I can show you what is meant by that. Suppose you are able to construct a structure as it is shown here. One film has a fixed magnetization, so it will not easily move or rotates the magnetization in an external field. It's supposed to be fixed. And then you add a free layer, have again an interlayer here, really to separate this free layer from this one, so it can really freely rotate its magnetization. And when you drive a strong enough current in this direction horizontally from one film to the other, then I can show you by the and you start here. Suppose you start with the anti-parallel magnetization alignment and apply this strong current. What you get is that the magnetization turns around. So you have a current-induced magnetic reversal of the magnetization due to the strong current. So this is one of the effects which were first predicted by Slanczewski and Berger in 1995, and later on the first experiment was done by Cartin et al. In this work here. Okay, so not only this, if you reverse now the current direction, and you start with the opposite magnetization direction, so this is the initial condition here, parallel, but you let the current flow in the opposite direction, then you observe that the free layer rotates into the anti-parallel alignment, as is now here demonstrated here. Okay, so that was the new effect, and we are working in Jülich now on this. And this is one of our examples where we observe the effect. I do not want to go into too much detail. What is plotted here is the differential resistivity as a function of the not the external field, but current. This is very important now. Now here we have on the axis, we have the current strengths, and at certain places of the current, we get jumps here in these curves, and they reflect the change, the rotation of the magnetization, only that it does not appear here in one big step from one orientation to the opposite, but it goes in steps on these places always by 90 degrees. So I do not want to go into the details. This is in the group of Daniel Björkler in Jülich now, one of these nice experiments where demonstrating this effect of this switching. Now we are also treating that in the group of Ricardo Hertel theoretically, and I like this in particular because now we are switching sort of back. We had before, I showed you the Landau-Lifshitz equation, which in this is this first part, but in order to treat this current-induced magnetic switching, one has to include now the damping term in the equation. One has also to include a term which describes the driving of the magnetization by that current, and then that picture here reveals how that works in detail. When you drive the magnetization with the external current, it starts to precess with ever higher amplitude. Yeah, okay, I know. Until the system goes into the opposite, and then finally it precesses again with a damping term until it is in the opposite direction. So that is, calculation reveals how that works, the switching works in detail. This is again our system, AA system, and the current flows like this. Okay, now, okay, so I'm now yes, at this point, and applications I would like to, the most important applications I think I should show you. There are now two types of sensors on the market. One which includes also anti-ferromagnetic interlayer coupling. Then you can have a multi-layer and you get a nice large signal. Then by the strength of the interlayer coupling, you can tailor also the resistivity curve. For example, here you have a broad resistivity curve. When you have strong coupling here, it requires a large field until you get the parallel alignment. So that becomes very broad here. Okay, so just to indicate the property of that. The other type of sensors which is on the market is called the spin valve type sensor. There you have a free layer and a fixed layer. You can fix that by means of so-called synthetic anti-ferromagnetic. I don't want to go into the details of that, but here you have the free layer, and that works in such a way that you can use that for monitoring mechanical rotations, for example, by adding to your object where you want to see the rotation a permanent magnet. That is always important for these mechanical applications. You need also a permanent magnet which you attach to the mechanical part which you want to monitor, and that permanent magnet rotates you the magnetization in the free film. The other one is fixed, and then you get the change in the angle between the magnetizations. That's what you need for the giant magnetoresistance effect. Okay, so with this I would like, this is the most important application, hard disk drives, where this type of spin valve sensor is used. And now I switch quickly to my last application. I think that is very important to talk about this one, because it's the now a very important application in medicine and biomedicine. And it works in conjunction with so-called magnetic beads here, application also of nanomagnetism and superparamagnetism. These are little spheres on the order of 1 micron in diameter, and you can prepare the surface of these beads in such a way that you attach molecules, like for example antibody molecules here, attached to the beads, and when you put that in a probe with blood or so, they attach then to the antigenes. And up to now, people use that for magnetic separation because the beads are separated from the rest of the sample by a magnetic field. You can collect them in one part of your glass here, as is indicated here. But now comes the application of the giant magnetoresistance field sensors. And I show for comparison the old application here in the hard disk drives. In the new application, you want to detect now the magnetic beads in that application. Now you want to have the sensor large. You want to have it very small here. Here you want to have it very large in order to be able to monitor many beads at the same time and get a good statistics. And in this way, by detecting the magnetic beads, you detect, in fact, the antigenes which you wanted to see in that particular experiment. Okay, so that is a new application, and I like that in comparison between here and here. Here we wanted to have the sensor as small as possible. Here we want to have it quite large in order to be able to detect many beads at the same time. And that brings me also to the end. This is the never-ending search in science. Here is the never-ending hydra, where you cut off one head, 2 new heads grow, and we have the same situation in science. When we solve one problem, 2 other problems show up, but it's also good for our young people that they always have something to do. And I thank you for your attention.